All right, we're back. My headphones died, but you want to make sure it's from big to small in this section. That's good. Can move forward, insert, sizing again. We're gonna do the back section now. Hold down your control. Apply divisions. 90. And this bias is like 6. Oh. And you see how the ones are increasing, so you want to select those. They're going big to small. Apply. Now everything's going finer as it approaches the cylinder, so that's better. Now again, insert sizing, and now we're going to select horizontal of these. I'm going to apply divisions 70. And then the bias is going to be centered. There. I could do like a 1.2. Now that we've done all the horizontal, we go to the more vertical sizing. Sorry, I did not apply yet. What's happening? Oh my god, so I don't know what happened there. Insert sizing. Apply. .48 divisions and a bias. It's going to be from big to small. Put like a 4. And the ones that are not going finer, I'm gonna select. So I'll got this one, and this one. Everything else is going finer. Apply. Good. Oh, forgot this one. Ah, it switched. Okay. All right. So you have to select them all at once. Good. And now we're going to do the final section here. And then final section is going to be insert sizing. Number of divisions, 70. A bias of 1. Well, I'm going to do a centered bias for this one again, as it's going through the cylinder. And it's going to be 1.2 again. Now, we'll insert another sizing for the diagonal. Cross sections. Apply. I'm going to do number of divisions by 50 with a bias. And it's going to be a descending order. 8. And again, make sure that it's going finer as it goes down to it. So these two sections need to be reversed. Perfect. Now you want to do an overall face mesh. Select all of them. Here, generate. And now that's generated. And we're going to name the inlet and outlet as well as upper and lower walls. Oh, spell that wrong. Now go to back workbench, make sure it's saved or updated, I have to say. Once you update it, and it's a check mark, you can close this mesh and start setup. Total precision. I'm gonna use about 3 processors. Otherwise, more than that usually gives me some licensing issue. Now, like I said before, my section will be more for plotting this velocity distribution on the surface of the cylinder, CP, and I think drag. Great. Now, I'm going to go here, and our first case that we're going to do is inviscid. And go down materials and make sure air is and as you can see for this one, you won't see viscosity because viscosity is 0, which makes Reynolds number infinite. All right, and then for the inlet, you want the freestone velocity to be 5. And then we want to update our residuals to be to the -6. And we can start to initialize this. That's good. It's not done yet. Oh, okay. You know what? Maybe it doesn't like running more than 2 processes because every time. All right, I'm gonna do 200 for the sake of time. Hopefully this doesn't crash again. It's not responding. I am pretty much tempted to just close this window. And I'm just gonna edit this. Guess until this closes. All right, we're gonna add this, and we're gonna keep it at 1 because my computer cannot handle it. All right, seems like it saved most of the things. Gonna go ahead and initialize. Oh, shit, it's so good. As you can see, it kind of converges very early on. But due to how we're still running it, even after that fact, like falsely reports it increasing. See right there. Alrighty. Now for A and B, would gather all the surfaces and in the graphics, but we're focused on the XY plots. So for this first thing that we want to get the pressure coefficient. You can save this as a inviscid. And you would write out to file. Here, I'm just showing you. So pressure coefficient, that wall surface body, save plot. So this is what you should see when you write it to file and save it to Excel to then compare. Close. Then I'm going to go down. Oh. So I want you to do the CP, which we just did. Well, let's go back and do the velocity distribution. Show you how that looks. New. And again, against the wall surface, you will save it somewhere in your computer so you can access it and export it to Excel. Yeah, same as that. That's how you should see. And then pressure, if you just look at pressure, should be the opposite. There. And then what else do they access for? Velocity, we did the CP, drag coefficients. So yeah, so for drag coefficients, you just go down to leave surfaces. Graphics. Which reports? Okay, yeah. So you go down for drag, go down here, and you print. And you see forces, relatively small. All right. That should be your drag. Right? Okay. Yeah. So I just showed you how to do the pressure coefficient, velocity distribution, and as well as the drag. And for the drag, you're only like taking the net force here and tabulating it. And you can calculate the Reynolds number. Because the viscosity is 0 for inviscid, you would just, that would mean that anything over 0 just means that the Reynolds number goes to infinity. I'll show you how it should look like for laminar. So for laminar, you want to keep the viscosity the same. Because you keep this the same as well as the viscosity, density, I mean. This should give you a Reynolds number for a velocity of 5, around 335,000. So that's still under the critical Reynolds number. Okay. Inlet should still be there because I haven't changed it. Residuals, and then you want to go initialize this all over again because we're doing a different flow. And then run a calculation. Okay, I guess I have to wait. Perfect. So for XY plots, now we're going to look at, get some new ones. So this is going to be CP laminar. And you would write it to file, to plot. Yeah, this is essentially how it looked like. And then for velocity, you see due to the no slip condition, what the heck? I scroll in, scroll. Okay, there. You'll see that their velocity at the surface will be 0. And that will be the same case when you do turbulent. And again, you would go down to forces to get that drag here. And you tabulate it, and Reynolds number should be 335,000, and that's under the critical. You go back here and then collect your, yeah, okay. And I changed the viscosity to be like 0.1 to make sure that Reynolds number is above the critical. So it should give you like 600,000 with a 1 viscosity. Make sure that that's saved. I did not save that. Close. Velocity and individuals don't change. You just want to go down and initialize all this. Run calculation. Alrighty. So, oh yeah. I know if I should show you quickly. Let's see. Somewhere. Nice little wake. Alright, but my focus is part C. We're gonna do velocity, wall surface, use save to write to file, and again, no condition, no velocity really. For pressure, you will see it act similarly to like the velocity. From the inviscid, like the pressure from the original one, the inviscid one, I mean. Yeah. And so you got the CP, you got the velocity, and the final thing that you want to get is forces again. And value here was for, yeah. Interesting. Okay, so that completes getting the velocity distribution, CP distribution, and then the drag coefficients from printing it out. Now we're going to compare the wake patterns of the drag coefficients. So when we first did all of these, I'm going to compare them to how okay, yeah, I'm going to have to cease sharing so I can yeah, now when you collect all the pressure coefficients, you essentially would put them all in here. So I put the inviscid flow in this category, the laminar, and then the turbulent flow for pressure coefficients. As you can see, the x-axis is actually pretty much the same for all. So I could plot them against each other. And these are the results for inviscid for blue, for orange turbulent, and then the green is our laminar. For drag comparisons, these are the values that we've gotten. Interestingly enough, this kind of switched off when I did this time. Not sure if I did anything different. And then for velocity comparisons, as you saw, for this changed for inviscid flow, all right, but for laminar and turbulent with 0, you can't really see the laminar line, but they are on top of each other, and 0 because of no slip condition. And now to compare the wake regions, I've put in my comparisons here. Since Reynolds number is infinity because viscosity is equal to 0, that means Reynolds is going to 0 infinity. It's infinite. Our wake region is a bit similar to what we expect for Reynolds number to be increasing. Now for laminar, because of viscosity is greater, we do see more of a larger wake region due to larger forces being experienced there. And that is evident here for how the wake regions and our online should be a bit larger as simplified here. And then because, so we do see vortices a lot in the wake. If you look at this is laminar. Vortices in here. And these are destination points. So that is true for the description. For turbulent, this is very tight. We do see a bit of vortices, but they're very extended, very like squashed down compared to the laminar, which is what we expect to happen. This one, the example here, ours couldn't find a 601, but with what we expect as turbulent transition from here to grit and beyond, right? We see a lot of turbulent vortices in the wake, so that's essentially what we are seeing here. And in comparison to the laminar, a lot tighter wake. And that completes my section of part 1.